Good afternoon. I'm Michael Wisnam from Bristol Composites Institute, and I'm delighted to welcome you to this Composites Perspective webinar. So at the Bristol Composites Institute, we believe in collaboration between industry and academia, and this series brings together speakers with different backgrounds from research and applications perspectives to talk about some of the challenges for composites. So the theme of this session is recycling of composites, and I'm delighted to have two excellent speakers here who will be joining us now. We have Tim Young, who's Head of Sustainable Technologies at the United Kingdom National Composites Centre, NCC, and he's also a visiting industrial professor at Bristol Composites Institute. He previously worked for NPL and has an engineering doctorate from Surrey University, and he's responsible for delivering composite solutions for net zero at the National Composites Centre, and also for the NCC's Sustainable Materials and Technology portfolio. And we have Nancy Sottos from the University of Illinois, Urbana, Champaign. She holds the Maybell Leland Swanland Endowed Chair in Materials Science and Engineering. She's the leader of the Autonomous Materials Systems Group at the Beckman Institute, and is also director of the program on regenerative energy efficient manufacturing of the Thermoset polymeric materials, which she's going to be talking to us about. And she's also director of the University of Illinois Spoke of the BP International Centre for Advanced Materials. She has the honor of being a member of both the US National Academy of Engineering and also the National Academy of Sciences. So just a couple of housekeeping points here. If you've got questions, please put them in the Q&A. Don't use the chat for that. Put the questions in the Q&A. You can do that anytime during the presentations or afterwards, and we'll have time after the presentations to answer some of those questions. We will be recording this session, and the video and the slides will be on the Bristol Composites Institute website afterwards. And you can also see there are past events from previous Composites Perspectives webinars on the website. So with that, I'd like to turn to our first speaker, Tim Young, who's going to talk about composites recycling. What should we do versus what can we do? So Tim, if you'd like to share your screen, over to you.
Hello, everybody. So good afternoon. My name's Tim Young. I'm Head of Sustainable Technologies at the National Composites Centre and a visiting industrial professor at the Bristol Composites Institute. I'm going to use the next 15 minutes to run through some of the work around circularity and in particular recycling, focusing really on what should we do. Before I dive into the work and the challenge statement, let me introduce the NCC. So the National Composites Centre is in Bristol. We're one of 7 high-value manufacturing catapults that form the largest advanced manufacturing capability in Europe. Our overall purpose is to support innovation and growth within the UK manufacturing industries and their supply chains. A key element of our work is addressing industrial transformation. It means resolving deep and complex technology challenges, supporting people with new capabilities that meet the requirements of future industries, and supporting the growth, resilience, and sustainability of our existing and new supply chains. An example from our impact report is we've resulted in a £59 million direct gross GVA per annum and seen 16% increase in supported organisations' turnover within 6 years. The NCC's core strength is as an innovation platform. We work across all industries, such as aerospace, and all forms of mobility, energy transition, such as wind and security and space. Our composite manufacturing capabilities flex themselves to supporting academic pull-through of new ideas, from statistical models, new material concepts, through to detailed designs and analysis, manufacturing, verification of parts, subsystems, and assembled products. This is underpinned by our cross-cutting areas of technology research, hydrogen, digital, and sustainability. With world-class manufacturing capabilities for composites, we've inherited some incredibly strong sustainability arguments, and our work supports key net zero technology developments in the 10-point plan for the green industrial revolution. However, as composites have exceptional performance and durability, we've engineered a material system that has massive benefits in the use phase, but that same durability means their derivation from non-renewable sources and complex end-of-life management is a serious challenge. It comes with the first key take-home. It is no longer acceptable to only focus on the in-use benefits of composites. What we're talking about, what else is there outside of the in-use benefits of composites? So over the next phase of the presentation, the outcomes of a body of work we've undertaken at the NCC to unpick what the real challenges are, not just to convince ourselves there's a problem, but to guide our recommendations based on facts for who, where, how, what, who, how, why, what, and more importantly, or most importantly, when. I'll then present the outcome of some work on the topic of the talk. What can we do versus what should we do? With a real focus on the circularity aspect on recycling. I appreciate there's a lot of aspects around defossilization and new material, but the purpose here at the moment is on the recycling end. So there's been various studies based on UK total composite waste. The exact numbers vary, but they all agree that whilst we have a problem now, the current manufacturing output, coupled with known order books, growth forecasts, and projected life expectancies of components and platforms, put the waste figure somewhere between 150 kiloton and 275 kiloton by 2035 in the UK. I'm also sharing two snapshots of sort of deep dive reviews on how the waste is manifested. Something that's particularly interesting to me that drop out of the wind study on the right hand side, and this is just from UK offshore blade waste, is that the volumes today might be small, but they grow exponentially over the next 2 decades. And whilst we have a focus on glass, the increasing length of blade and use of carbon means that optimal solutions today for wind and other industries might actually need a rethink in 10 to 20 years. And it leads us to a big question. Is it a one-size-fits-all approach? So what are we doing? What's the backdrop to some of these challenges? What have we been looking at the NCC? So the NCC, National Composites Centre, has committed a significant portion of its available grants to build capabilities in sustainability. So on the screen in front, I'm sharing a series of programs and projects around circularity, from network and review-based activities such as Rediscover, a network across with representatives from a multitude of industries and academia, trying to highlight exactly what the challenges were. We've run 4 years of multi-sectoral pre-competitive research on recycling. It's covered everything from shredding to manufacturing of second life parts. We're working across consumable waste. We've made some real strides, which we plan to investigate further. I'm going to touch on the continuous fiber tank recycling work in a later slide. But overall, wherever possible, we've tried to maintain a technology agnostic approach to recycling, and in particular to the reclamation technologies. So I'm going to share some data and some of our positions and understanding going forward. But the last 4 years assessing and stress testing different technology options has been across manufacturing consumables through to full wind blade studies. And it's given us some unique insights into the practicality and, more importantly, the room for innovation. So it might be a bit of a statement of the obvious, but the recycling and end of life scenario is a little bit complicated. We I'm a technology focused person, so I have a tendency to get trapped into the reclamation process. So that's the recycling stage 2 bit here. And therefore we end up comparing different routes as though they're all the same. There are key differences between reclamation processes, but it isn't a one size fits all approach. What is clear to me from this particular flowchart, and it's one of many, is that the options available for recycling are entirely dependent on how the materials are handled in the earlier stages. So in the UK, we've got a waste setup where material is shredded very early on, mainly because metallics and other valuable materials are easily extracted. But by doing so, we reduce the choices and options for retaining both the value and reducing unintended harm down the line. So it restricts our options when it comes to composites. So how can we change it? So one of the areas we at the NCC hope to make a difference is to develop the product applications and therefore market for recycled materials, both fibre and matrix. So this is one of our flagship projects alongside the Henry Royce, Signet TechSkimp and the National Physical Laboratory. The aim here is to develop quality assurance capabilities for recycled continuous carbon fibre. And what I'd like to do and see is real life data at scale and rate that can be used by designers for the next product. If the uptake of carbon fibre is half of what is predicted, then recycled materials in application, and I mean the right application, will substantially reduce the system burden on our environment. Within SUSWIND, so that's a programme at the NCC with a multitude of partners, industry and other RTOs and funders and asset owners. We developed a series of very specific scenarios to understand what pathways for recycling might result in the best outcome in terms of global warming potential and mass balance. We first studied this for a wind blade system, and it was apparent that certain routes weren't viable, such as cement kiln, either because of the presence of PVC coatings in legacy blades or carbon in future designs. And it's raised a key recommendation that to achieve the optimal outcome, dismantling and separation of material types is required as early on in the process as is feasible, but ideally well before the system is shredded. And to make this clear distinction, cement kiln for glass was viable, but the PVC coatings weren't. So we have an issue that we need to really focus on the early stages as well as just the reclamation processes. So just on the glass side, so that's the two top charts here. The gains or costs for glass recycling are quite small, but the volumes are really large. So mechanical recovery in cement kilns look like the most optimal today. So this is from data about 2022, particularly if the recovered material replaces and therefore reduces the amount of virgin material otherwise consumed or made. It's worth noting that this is a bit of a mass balance argument rather than just a global warming potential one. And there's a caveat on cement kilns. Cement kilns come a close second to mechanical recovery if the kilns are set up to receive them and the kilns are utilising coal and they aren't already using municipal or biofuels. For carbon, whilst the volumes are smaller than that of glass, the global warming potential of producing virgin fibres is so sufficient that reclamation processes like pyrolysis and all the way through to pyrolysis result in some really big savings, potential savings on GWP, global warming potential. So it's worth noting that these are a snapshot in time. The charts will look different in the future state, particularly as technology is scaled and energy reduced. Therefore, we need to start moving towards target-based approaches. We can use mechanical and cement routes now for glass, but we'll need to reduce the energy intensity of the technologies to fit a future state. And we believe that this type of planning needs to be time-bound and start setting targets and targets for technology and supply chain development. So leads us to an earlier question, what should we do? So GRP, glass fiber reinforced plastic, dominates by volume and has a significant landfill burden. And CFRP has a larger potential to reduce global greenhouse gas emissions. It suggests to me two things. We should use what capabilities we have today to reduce the burden of both materials. It means for today, adopting cement and mechanical recovery process for GFRP. It means utilizing and developing technology approaches for carbon reinforced plastic, and then applying those to the same technologies for GFRP as the existing routes phase out. As a summary, the data doesn't suggest that technical routes like pyrolysis shouldn't be used for glass, merely that they need development and scale in order to represent a better environmental option than the mechanical routes, for example. This is why the NCC's focus is to develop these technologies first with carbon in mind, as well as to develop the surrounding system and economic cases to support the supply chains. How can we support those developing glass-based recovery methods based on the learnings we take from carbon? This means everything from separation, reformatting, quality assurance, and all that's needed to see the recovered materials, both fiber and matrices, utilized to see them utilized in future applications. As a note on the matrices, over the last few years, we've seen an increase in the number of recyclable matrices, bio-based matrices, and other variations. These materials aren't always being developed in tandem with the supply chain or the technologies needed to manage them end of life. In the earlier scenarios, the matrix is either a waste byproduct or fuel in the process. And what we've proven is that glass and carbon recovery is technically viable. There's a significant opportunity to innovate and build the supply chains now and for a future state. But a key part of it is to innovate in resin recovery, both to support the economic case, but also to boost circularity and reduce the global warming potential of composites. So I just want to leave you with a few takeaways from our findings. We need to innovate across all technologies. We need to focus on target-driven approaches. Global warming potential is one metric, but we need to ensure that its priority doesn't inhibit us from taking any action at all. We can resort back to the use case argument. Composites do and are essential in the delivery of key products needed for the 10-point plan. What we should do is to innovate. Some routes have far better potential than we are realizing today. Collaboration is needed to pull on these supply chains, as today the numbers might be small, but the cumulative impact will require far more supply chain and technical capabilities in the future. So that's it from me. Thank you very much for listening. And any questions?
Thank you very much, Tim. It's a really interesting overview of the topic. And we are open for questions. If you want to put questions, please put them in the Q&A box on Zoom. We don't have any questions yet, but please put them in now and at any time during the rest of the session. Tim, can I perhaps just ask you one thing myself with regard to what happens with the recycled fibers? I've heard people say that there really isn't enough of a market to actually for companies to make money out of taking those recycled fibers and actually using them. What do you think about that? Is that an issue at the moment?
I mean, yes. I think there's an unrealized market, Michael. Part of the challenge is less about whether or not the market's there, and it's part around the practicalities and the acceptability. Are we producing the recycled fiber in a way and as an output that designers know and are able to use effectively? Have we got the confidence in their use? Those are the kind of questions that we've been exploring, and it's part of the reason why we've started to focus one of our big interventions on continuous fiber to eliminate some of the variables around acceptability and to start moving this dial on a little bit so that you can start to see more products because you have a higher confidence in the material because it's in a format people are willing to use. and take those learnings and apply them elsewhere.
Yeah, thanks. We do have one question that's come in here, which I don't know whether you can answer this one. What is the current ratio of landfill to incineration to recycling globally for CFRP? Any idea on that one? I'll put you on the spot.
I'm afraid off the top of my head, I couldn't tell you. I'd need to go through the data.
That was a bit of a difficult question, but it's an interesting one. And
I'm sure if I know who's asked it, we can dig out the numbers for you. But
yeah, unfortunately, there was no name on that one. But okay, one from Beth and Charles. Thank you for the presentation. As technology innovates and the composition of composites changes, how can we apply a long-term recycling strategy for different materials?
I'm not sure I know how to unpick the question, Michael. Do you mind asking again? Sorry.
Yes. How can we apply a long-term recycling strategy for different materials? Referring also to the composition of composites changing.
So I think what we're finding is that we need a strategy for each material if we want to get the best outcome. But what we need to be focusing rather than how can I manage the waste that I'm creating to what are the types of markets and products, whether it's be from fiber through to resins into new chemicals, that I therefore need to design my materials from so that I can then recycle them and they have a second life. And that might mean phasing out things like PVC in terms of coatings so that it allows new routes. But I think what we need to do is to start designing those material systems for recycling in terms of a strategy, rather than trying to devise a recycling strategy for what we've already got.
Okay, thank you. So we do have now a few questions starting to come in, but I think we'll put a pause on that for the time being, and we'll move over to our second speaker, Nancy, if you'd like to share your screen and give us your presentation on regenerative energy efficient manufacturing of thermoset polymers and composites. And please keep putting the questions in and we'll take them up after this presentation. Thank you. Over to you, Nancy.
Hey, thank you. Can you see the screen? Can you see it full screen?
Yes, that's fine.
All right, great. So I'll get started. I'm Nancy Sottos, was introduced earlier from the University of Illinois, Urbana, Champaign, and happy to talk to you today about our work on regenerative energy efficient manufacturing of thermoset polymeric materials and composites. So it's a short talk, but I even put outlines on short talks. I just want to provide some motivation for the strategy that we are pursuing at Illinois. Talk about a rapid curing technique by frontal polymerization, and then finish up with and continue on just how we apply this to energy efficient manufacturing of composites, and then finish up with how we use this to impart deconstruction and regenerative strategies for composites. So starting out with the background, I think we know that thermoset polymer composite structures, this was outlined very nicely in Tim's talk. We've designed them to have high strength, high stiffness, and last for 30 years in some pretty harsh conditions. We also know that these materials, in order to get these properties, have a very energy intensive manufacturing process. The cure times are long in order to get the cross-linking up. They're energy intensive. The part gets larger, the energy keeps scaling with the part size. And also, there's really no viable end-of-life strategies. And again, Tim's talk outlined really all the different mechanisms that are going on. There are many, many groups working on this, but it is definitely expensive and complex to upcycle, recycle composite materials at this point, and just a really good opportunity for research in this field. Like any complex problem, these require collaborations. We have a center at Illinois, which we fondly called REMAT, and these are some of the key faculty and researchers in that center. So I'm going to present work from with a lot of different contributions, and I'll show the students at the end. And I won't take time to read everyone on this slide, just that you know that it's an important team approach to the problem that involves chemistry, manufacturing, material science. So just a little bit about our vision of the center. This isn't where we're at yet, but just a little bit about the philosophy of how we're approaching this problem of circularizing the life cycle of thermoset polymers. So it starts with a manufacturing platform based on frontal polymerization. The idea is to be able to efficiently manufacture composites out of autoclave using techniques that save energy and time. My image here shows an additive technique. Unfortunately, I won't be able to talk about what we're doing in additive this morning. I stuck with just more traditional ways of making composites, but that's something that we're doing. Then our approach, and there are many approaches kind of being considered for thermosets right now, but what we're looking at is a programmed deconstruction. So that is, at the beginning, we impart a cleavable comonomer into the network so that really at the right time, you can trigger deconstruction into oligomeric fragments. And then the goal is to take those fragments, basically get out recover the useful units of oligomers, as well as any reinforcement that you've put in. And of course, the goal is to maintain properties as you're putting in these deconstruction units. And that's been I'll talk about some of the challenges of what happens when you drop these units into a thermosetting system. And so let me start out talking about the manufacturing process, because I think that any good deconstruction strategy really does start at the beginning in the initial design and manufacturing of the material. We are using a process called frontal ring opening metathesis polymerization to make our composites. And if you haven't heard of this, frontal polymerization is a process by which you go from monomer to polymer using the inherent exothermic reaction of the material. And all you really need to do is add a small amount of heat at the beginning. See if I get that. And then that causes the monomer to locally convert to polymer. Heat is generated in the process, it diffuses forward, and it sets up a propagating front. And you can see in the image above, it's like dominoes. You have to just put a little bit of energy in, and then the exothermic reaction takes place and just moves, giving you a uniform reaction front when you're doing everything correctly. In a test tube, it looks like the images you see on the right. You have a uniform, the heat has been applied at the top, there's a uniform propagating front, and on the right you see the IR video, and you can see there's quite a bit of heat generated, and you can see it diffusing forward and moving with the front as it goes down, and then basically you convert to 100% polymer. The chemistry that we are using is not an epoxy. It is a cyclic olefin. There's a lot of advantages to exploring this strategy in cyclic olefins. And we are in particular looking at the frontal ring opening metathesis polymerization. We use the word FROMP for short. It's kind of a funny acronym of dicyclopentadiene. This is a commercially used monomer. There's actually people making wind turbine, ExxonMobil is now making wind turbine blades with dicyclopentadiene. This just shows the specifics. The initiator that we're using is Grubb's second generation catalyst, and this inhibitor is also very important for pot life. What's nice about using a poly-DCPD is that once you cure it up, it's got really nice properties comparable to a aerospace grade epoxy, except that it is actually quite a bit tougher. It has a much higher fracture toughness. Modulus is a tiny bit lower than most epoxies, and significantly higher fracture toughness. And it's got actually a well-defined yield, which is also interesting in a cross-link system. As I mentioned, the key to this all, I'm going to go over the chemistry very quickly, is this inhibitor, because basically you mix all these components together to formulate it. It's an active system that could react, but you have an inhibitor that gives you some time, some pot life in order to get it, infuse into a composite or print it. And so we've worked a lot with these phosphite inhibitors that can give us with the right formulation, up to 30 hours of working time. And so what this means when we have the inhibitor with the DCPD is that there is a slow gelation stage, which can be quite useful for printing, or if we're infusing, we've got to do it before it gels. And we create the thermoset. And what you just see here is a plot of the storage modulus and the loss modulus as a function of time. It's a clear crossover point. Our crossover point fortuitously is very close to the actual gel point when the viscosity starts going up. And in these different stages, early on with this particular formulation, if we work before 5 hours, we're able to infuse this resin into composites. We have plenty of time to do that and create high quality composites. That's what I'm going to talk about today. If you wait a little bit longer and you get into the gel state, you have a material that's has the right rheology for 3D printing. That's something I'm not going to talk about. And of course, if you wait even longer, in this case, it was 11 hours of pot life, you won't get this frontal, there's a background reaction that occurs and you just kind of get an undesirable material and no capability for frontal polymerization. So let me tell you about how we've put this into composites. We have we've been using, one technique we've been using is vacuum-assisted resin transfer molding, or VARDM for short. Basically, we infuse the resin in. It's got DCPD has a very, very low viscosity, so it's very amenable to things like VARDM. We can use a traditional bagging technique and just say, the first thing we did was use an edge trigger. And we're able to process a panel very quickly. Let me show you a video of this. It's going to trigger along this left edge. It's in this case, a 10 by 20 centimeter panel. That's the trigger. Now there's just a little bit of energy added in. It's actually 5 seconds the resistive heater is on. And then that's enough to locally heat it and propagate this front. This is kind of dramatic as we propagate the front along the panel, but that's the way we did it first. And you're able to cure this panel in 2 minutes. And you can we've made up to 35 by 35 centimeters. And you can get kind of complex shapes. You can have the front travel along a corrugation in the flat panel. I just show cross section there. It's a nice material. These are all woven that we've looked at. 51% volume fraction in these early ones, low void content, and a pretty good TG, 134C, a little bit below that of the neat resin system. That's due to these early processing methods. The properties of the system are pretty good. This is the frontally cured composite compared to a kind of an oven cure of the same material, compared to a oven cure, autoclave cure of a similar epoxy, our comparison aerospace grade epoxy. It's a little bit under the mark, but pretty good. And there's things that we've been working on along the way about increasing glass transition temperature. The fibers are all sized for epoxide, so we've got lots of challenges on fiber matrix interface that we've been working on. But overall, a nice result. Since that time, it isn't really practical to move the front along the panel. You can actually do this even more quickly if you do a through thickness cure, so the heat comes up through the bottom just through the thickness. And if you add a little more heat, so there's a little more energy in, as I show here, you can cure the composite through the thickness. You see the IR image of just the wave coming through. And this can produce actually very nice composites. We can get the TGs well up over 150 to 160 degrees C. The triggers are on for seconds to minutes. And we can get high volume fraction, 65% volume fraction. So it's a very fast way of making a nice composite without an autoclave. If you add, the key to getting the volume fraction up is to add some compaction, as you see in the image there. And just as comparison, this is, basically we look at frontal curing is the green curve here. If you look at the temperature time curve, I compare it to some more snap cure systems that are on the market currently, which still require heat up and a little bit longer times. And then of course, a more traditional autoclave cure. So there's a lot of time and energy saved on the way in terms of sustainability. But now to kind of tie in terms of just looking at ways to recycle, reclaim composite materials, I want to just start to discuss some of the deconstruction strategies we've used for this polydicyclopentadiene thermoset. So crosslink network, normally we've been taught this is not deconstructible. It's a permanent network. That's what gives us those great properties. And PDCBD is no exception. And we've been teaming with Jeremiah Johnson's group at MIT, and Jeremiah Johnson is in the chemistry department there and has been working on these cleavable strategies. Actually, this is a great COVID collaboration that started over Zoom. But the idea is to introduce these cleavable groups into the backbone of the monomers. And the idea is that can we also energy efficiently frontally polymerize these systems. And then basically we have these groups that are cleavable by hydrolysis that will let us recover oligomeric fragments. And so this is basically the idea. After cleaving, you have a very triggered degradation. You have the oligomeric fragments with some very reactive handles on them that can be upcycled into something else. So does this work? We examined and published a pretty recent paper on this, 4 different cleavable comonomers that are compatible with our ARM monomer. I show them here. These are cyclic silyl ethers and cyclic acetyl 7- and 8-member rings. And basically the take is as we add amounts of comonomer in this, it actually reduces the ability to frontally polymerize. So we want to add as little as possible. But what the graph on the right shows is that, yes, I can add this comonomer. It still will frontally polymerize. It slows down as you add more, but you really don't want to be adding 20 mole% of the comonomer. I want to stay in this window, as you'll see from the properties. It turns out that these 7- and 8-member silyl ethers incorporate best into the network and actually are the most efficient at deconstruction. Let me show you a little bit about the deconstruction process. These are just little scint vials with pure polymer in them. This has been frontally polymerized at 0 hours. And you can see there's different amounts of the cleavable comonomer in here. So 0%, you would expect no deconstruction because that's a permanent network. And then as you move along with time, what you can see is that these materials with varying amounts, this is actually after 16 hours. I don't know where the 16 hours disappeared to on here. You can see that with 5% mole% of the cleavable comonomer, you get full dissolution of the thermoset network, which is quite extraordinary. And on the right, you see just plots of residual mass as a function of comonomer. And once you get to this 5 mole% comonomer for the 7- and 8-member cyclic silyl ethers, you really got no residual mass in the scint vial, and you've got a fully deconstructed thermoset material, which I find extraordinary. No heat during this process. It's just time for the hydrolysis to happen. The downside of this, though, is that you do take a reduction in some of the network properties of the material. There is a reduction in glass transition temperature because this cyclic, the cleavable comonomer is kind of a big molecule. You see the TG go down. There's not a big effect at small comonomer concentrations on elastic modulus and yield strength, which is good. So it's mostly this TG. And so we've chosen to operate in here. We've actually, I can give a longer talk. There's all sorts of clever ways to bring this TG back up with cleavable cross-linkers. That's a pretty complex chemistry, but it's really something that can bring the TG back up over 150C again. But let me show you how also the upcycling works of the fragments. So basically, once we deconstruct this material, we're left with the oligomeric fragments. And one of the first things that we did is, well, what can we make of them? At this point, they can't go back to dicyclopentadiene. And what we added was a catalyst. And the idea is that we're going to bring this system into, so by adding isocyanate and catalyst, we can bring this system back to another useful polymer. In this case, we've made it into polyurethane. And it actually makes a really nice polyurethane film. Now, this polyurethane is not recyclable, so we've just sort of gone like 3/4 of a cycle, but it's a huge start because this polyurethane, this is the blue curve, this is just the tan delta to show you the TG. The upcycled material that comes from these oligomeric fragments that we recovered actually has a higher glass transition temperature. It's really quite a good material that we've made. And the strategy as we move forward has been to, we're actually starting to add these fragments in to pure monomer, just like you do with recycled polymers. And we've actually gotten, I haven't put the data in this talk, we can put 30% of the recovered oligomers into monomer and get a pretty good polymer out. And so there's a lot of really interesting promise on making this circular as we explore different cross-linkers and different cleavable comonomers for this system. Let me finish. I know Michael's wanting me to finish up with the composite story. The idea is that we can take this same resin system that we looked at quite extensively, its deconstruction, and put it into a carbon fiber reinforced composite, similar to using the techniques I showed you before, using a very rapid through thickness cure. So we make this thing in about less than 2 minutes. In this case, we started out with a lot of comonomer. This is the 10 mol%. This is to make sure it deconstructs. You can see that we've lost some properties from initially. We've got a TG of 105. So still not a bad material, though. We're up over 100 C for our glass transition temperature. It's got nice properties. It's actually a very nice composite. And I just show the DMA data here on the right, the storage modulus and the tan delta as a function of temperature. So can we deconstruct this? So this is immersion. This is basically the hydrolysis process. We're taking 1 molar of HCl in CPME, and we basically take the whole composite, soak it, and then what's interesting, I love this image, is that you can just start to see the fibers can come out whole and undamaged. And basically we can recover the carbon fabric, which was a discussion in the prior talk. And we can grab out the oligomeric fragments from the solution after this is done. And again, I'm not going to show the XBS of the fibers. They're remarkably clean. This is just an SEM to show you that. And we're in the process of doing the characterization on the tensile strength, but actually it's really promising. There's almost no damage to these fibers that we can see. And in fact, they're super clean. They don't have sizing on them anymore, which is also, I think, a benefit. And so this is sort of the strategy is this regenerative composite manufacturing, where you have basically combine these things together, deconstruct, and you can, right now we can take the matrix into other monomers. The interesting thing is that we can actually get these carbon fibers out and put them into another composite. And that's what this last slide is that here's the pink curve is this original composite. It's got pretty good properties, not the best, but it's I think a really interesting first step. Then I show you the the recovered, this is a composite with a, we've taken the fibers and rescued them out of the original, put them in a second generation composite, all new monomer in there, which is also still deconstructible. And the recovered material has the same elastic and properties and glass transition temperature as the initial. And so that's a great story. The gold curve here is a different control that we've been looking at. And so just let me end there on that, you know, hopefully convince you that frontal polymerization is an interesting process for composites. We can make them quickly out of autoclave with nice properties. We've been able to impart this cleavable comonomer using that enables deconstruction of the neat resin and the composite. And we've successfully recovered fibers and reprocessed into new composites with comparable properties. So that's the team here at Illinois. I want to acknowledge our funding sources: Department of Energy, EFRC, the REMAT Center, Boeing, AFOSR, and NSF. And I'm going to put this up while there's questions. These are all the different PhD students and postdocs that have contributed to this work. The top row are all the ones working on the polymer, and the bottom ones are all working on the composite. So I'll take any questions. And I did go over a little bit, sorry.
Well, that's fine. Thank you very much, Nancy. That was a really interesting talk, and it's very exciting to see what can be done, both in terms of the polymerization, the reduction in manufacturing time and the energy, as well as recycling. So thank you very much for that. So please put in your questions. And we've got one here for you, Nancy, about how to shape the thermal trigger for complex 3D parts.
So that's placing the trigger is a little bit like a molding process, because you can have multiple triggers, you can have fronts meet, but the you know, you are going to have you do have to worry about the heat when the two fronts come together. So there's a little bit of again design, much like when you have injection from two different ports, and the fronts the flow fronts have to meet, so to speak. So I think that basically you want to keep it simple with the shortest path and the least amount of energy. So it's a bit of an optimization problem, but certainly as the part gets big, it's hard to have like a heat blanket that can cover the entire thing. So you are going to have to think about multiple triggers through it.
Thank you.
I hope that answers the question.
Yeah, from Sottos, saying it's a wonderful presentation, and asking about what do you see as the biggest hurdles in your quest to implement recycling strategies?
So I think in terms of the work we're doing, what we see as big hurdles as once you start adding the cleavable comonomers in, you do change the processing parameters. So understanding the changes in rheology, so it gels differently than the material, you know, and the cure time, the pot life, all the things that matter for manufacturing change when you put these cleavable units in. So being able to characterize and understand that. The second is maintaining properties, keeping you know, we want these things to have high TG and be durable for 30 years. So I think that's a key challenge. And then certainly being able to keep the reactive fragments active so that they can come back into a full cycle. You know, just having the right groups, the right chemistry, but you know, so there's a lot to do. So there's challenges, I think, on all fronts, but what's been interesting is that also we're employing, like many people, machine learning schemes on how to quickly assess how these different comonomers affect these different things that I just mentioned. And so I think being able to test large data sets is also important to deploy this more quickly.
Thank you. I'd like to bring Tim back in now. And Nancy, if you'd like to stop sharing your screen, please. And we can continue the questions and open it up. I'd like to to take a previous question which we had for Tim from Jolie. Do you have any perspectives in thermoplastic composites recycling? And either of you can take this question, but I'll ask Tim first to respond.
Yes, it's something we've been debating a lot about and trying to understand how best to move forward. The reality is that solutions exist, but I'd bring it down to the automotive challenge. I went to visit a recycler and was stunned the fact that we're baling cars and therefore crushing and shredding the thermoplastics and systems into mixed stuff with carpet before we've had a chance to recycle it. And so my perception is we can technically do it, but we haven't set up the supply chain. What we need to do is start focusing on getting products made with thermoplastic composite recyclate so that we can start make the economic case to start or to capture that material before it disappears into the stream, into the waste stream.
Yeah, thank you. Question here from Bing about asking how difficult it is to apply the frontal curing technique to large structures.
So in principle, it should not be hard at all, as long as you can propagate the front. And again, the goal is to move through the thinnest dimension is your best strategy. So to propagate it through the thickness of a large structure should be relatively, it should mimic what we do in the panels. We have. Sometimes every once in a while we think about doing a demonstration piece on a large part. It should. What's interesting is that the energy in is still small, right? It doesn't scale with part size like an autoclave. But again, you have to think about where, as I said before, where you place the triggers. If you need multiple ones on a say a wind turbine blade or something of that magnitude. You wouldn't want to wait for the front to propagate, or if you're able to heat the whole underside of the blade like you can now, it would be the same. It would be just minutes to cure it.
So Tim, a couple of questions here, which I see you've actually answered on in the question. I'm not quite sure whether everybody can see those. Would you like to comment on any of those points which have been raised that you've answered? Reformatting of fibers.
Yeah, sure. Well, why don't I start with the shorter one then? So Jack Cullinan asked a couple of very pertinent questions, really. The first was around are the numbers around CFRP recycling assuming that we're replacing virgin materials? The answer is yes. That's got to be the ambition. The second question was whether or not it's realistic for aerospace applications. There are some discrete examples of non-critical parts, but again, it's got to be the ambition. We have there is viability in terms of recovered fiber. What I'd say at the moment is that we're also seeing some really interesting results based on measuring the recovered chemicals that come off from things like pyrolysis oils or in flue gases, etc., that could be used back into things like SAF fuels all the way through to new materials. So this is an area that we're going to be exploring a lot. The second answer is a lot longer, which was from Malcolm Forsyth. So I've typed it in, but effectively we are doing a lot of work around reformatting. Most of the reformatting capabilities are in industry or around different RTOs. The ones that are closest to us at the NCC probably are the Hyperdiff example. So that's the short fiber alignment technology into aligned tape. A lot of work on that. But our real focus is on the continuous fiber so that we can minimize those variables and then work out how do we get the quality assurance and the acceptability for reformatted materials as well.
Thanks, Tim. So another comment question from for Nancy. work's really impressive, especially the cure time. Could you explain a bit more about how this super fast speed is achieved? Is the time enough for the chemical reaction? Is that possible technique go to the pre-preg manufacturing?
So, yeah, those are good questions. So the short answer is that the fast speed for this is in the chemistry. The monomer that we're using has these like incredibly strained double bonds in it. So some people may have seen some frontal curing for epoxides. Those are cationic systems, and actually they don't move this quickly and as efficiently as in the cyclic olefins do. But the idea is basically there's enough small amount of heat in, there's quite a bit of heat generated, and you want front speeds that move at over 1 millimeter a second. That's usually gets you into like a good processing range for a composite. Not all things that frontally polymerize move that quickly. So if you're going through the thickness and you just have a few millimeters to go through, that's basically how you get those cure times. Interestingly, also, this reaction is so efficient, the way the catalyst acts on these cyclic rings to open them up. You do get full curing in this small amount as this heat wave moves through the material. So it is remarkable that the chemistry and the kinetics are so fast that it's able to do this. The properties, again, it's a really tough material system. It is not a brittle material system that's left after this front goes through. It's everything you want out of a fully cured thermoset material. In terms of pre-pregging, so the traditional pre-pregging is not as viable, because again, we want it's tied to the stability of the catalyst. We can certainly stabilize the resin system for long periods of time. Instead of a traditional pre-pregging approach, and the reason is because the activity of the carbon fibers kind of messes with the inhibition of the polymer and working time. So basically we have months of pre-preg, but not a year of pre-preg. The other thing that we've done, though, is that I can, and anyone that knows my background in self-healing materials, I can encapsulate this catalyst in a material. I can actually stabilize the catalyst fully and then leave it in the system so that when the front comes through, the catalyst isn't released till the front comes through. And those are resulting in remarkably stable systems, right? So basically you can just leave the catalyst and the sitting in the resin system till you're ready to process without having to refrigerate it, which is also kind of fascinating to me. So that's on
We're nearly out of time. We still have a few questions, but I think we need to bring things to a close. Do either of you have any final comments you'd like to make before we finish?
I see that.
No, just thank you. Thanks for the opportunity. It's been good.
Well, thank you both for sparing your time to give us these both very interesting, quite different and complementary presentations. So the slides will be on the website shortly. So thank you very much for you two for presenting. Thank you for our audience for participating, and look out for the next Composites Perspectives seminar, which will take place in the autumn on composites manufacturing process simulation. So thank you very much and goodbye.